Welcome, 8th graders. I am so incredibly excited to be here with you today for this explainer. We're talking about something every single one of you has experienced in the science lab: precision and reliability. Honestly, you can think of this as the absolute foundation of scientific integrity. We're going to look at what makes science actually work and, well, more importantly, what happens when it doesn't. Let me just ask you a question right up front. Have you ever followed all the instructions in science class, done literally everything your teacher asked, measured everything out perfectly, but still somehow ended up with the completely wrong answer? Yeah, me too. It's incredibly frustrating, right? You mix the chemicals, you track the time, but your results look absolutely nothing like what's in the textbook. Why does that happen? Why do our experiments actually fail? Section 1. The quest for perfect data. Okay, let's dive into this. Whether you're a middle school student doing a chemistry lab or a top-tier engineer working at NASA, the goal of all science and engineering is exactly the same: finding the truth through reliable data. Data is basically the map that helps us navigate the physical world. But here's the big idea, so listen closely. Every single experiment has sources of error. Every single one. Errors are completely normal. Even the best, most heavily funded scientists in the world get errors. But what separates good science from bad science is recognizing those errors and actively working to reduce them. Because if we don't catch them, we might draw entirely incorrect conclusions about how the world works. Section 2. 3 culprits of error. All right, it's time to put on our detective hats and identify the main suspects that are constantly trying to sabotage our data. Our first culprit: random error. These are errors that happen entirely by chance. They're basically unpredictable flukes. You didn't do anything intentionally wrong. They're just tiny, uncontrollable variations that naturally occur during any experiment. To really bring this to life, imagine you're measuring reaction time in class. You drop a ruler and your partner catches it while you click a stopwatch. Now, sometimes you're going to hit that timer button a fraction of a second too early, and sometimes a fraction of a second too late. Those tiny, uncontrollable differences, those are random errors. They just happen purely by chance. Now, what's really interesting about this slide is our second culprit: systematic error. Unlike random errors, systematic errors are incredibly sneaky. Why? Because they happen consistently. They're often built right into the equipment you're using or even the procedure itself. Think about a faulty thermometer, for example. Let's say you have a thermometer that always reads exactly 2 degrees Celsius too high because it just wasn't zeroed properly. You could be the most careful scientist in the world, taking perfect readings every single time, but unless you realize the tool is broken and recalibrate it, every single reading you write down is going to be exactly 2 degrees wrong. That is a systematic error. And this brilliantly illustrates the fundamental difference, which, by the way, is going to be absolutely perfect for your homework. On one hand, we have random error. It happens by chance, swinging a little high or a little low, totally unpredictably. On the other hand, systematic error, a consistent, built-in flaw that pushes all your data in the exact same wrong direction every single time. And, well, that brings us to the final culprit: human error. Yep, that's right. Sometimes the problem is just us. These are physical mistakes we make in our own technique or our observation while actually doing the experiment. Remember being in chemistry class, pouring liquid into a graduated cylinder? You know how the top of the liquid forms that little curve called a meniscus? If you look at it from a high angle or a low angle, instead of exactly at eye level, you're going to misread the volume. Just reading the line wrong throws off your entire experiment. That is a classic human error. Let's move to section 3 and see how this builds: how to fix errors. Okay, so we've identified the suspects sabotaging our data, but we are absolutely not helpless here. So the crucial point is how we build reliability back in. Step 1, calibrate your equipment. Always check your scales and thermometers before you start. Step 2, ensure consistent procedures. Do the experiment the exact same way every single time. And step 3, repeat trials. Don't just do an experiment once and call it a day. Do it multiple times to make sure your results actually hold up. Think of this as your perfect visual study guide. To conquer bad data, we just match the specific error to the specific fix. To correct random errors, we average our multiple repeated trials so those tiny chance variations basically just cancel each other out. To fix systematic errors, we recalibrate the faulty equipment. And to fix human error, we get proper training and we constantly double-check our technique. Keeping these relationships in mind is honestly the best way to evaluate data critically and absolutely crush your homework later. Section 4, Science, Integrity, and Life. So, we've spent all this time talking about scientific integrity in the laboratory, making sure our data is true, honest, and reliable. But that exact same principle of integrity extends way beyond the walls of your science classroom. Moving out into the real world, Proverbs chapter 10, verse 9 states, "The one who deals honestly will live securely." Just think about how perfectly that parallels what we just learned. Just as honest, careful data collection makes an experiment secure and reliable, living a life of honesty makes your own foundation secure. You don't have to constantly worry about hiding mistakes or, fudging the numbers in life. Honest actions lead to a secure path. And this brings us right to the core philosophy of the Heroesmart Academy Godly Learners series. Their curriculum intentionally intertwines biblical morality with education. They make the argument that education without morality can actually be really harmful. I mean, what is the point of getting straight A's and being perfectly educated if you lack the moral foundation to make good choices? If you use all that intelligence to make bad choices that end up hurting yourself or the people around you, well, that education hasn't really served its ultimate purpose, has it? On the flip side, the curriculum highlights a really beautiful promise from Romans 8, verses 6 and 7, which assures peace of mind to everyone who keeps their mind spiritual. Combining the pursuit of knowledge with a solid moral spiritual grounding, it results in way more than just a good grade on a report card. It aims to provide actual true peace of mind. And that is what the creators of this series believe is the direct, lived experience of people who engage with learning in this really holistic, truthful way. So, what does this all mean for you? I want to leave you with a final, powerful question. You now know exactly how to find the truth in the science lab. You know how to identify errors, calibrate your tools, and act with scientific integrity to get totally reliable data. But how are you going to apply this integrity to your own life? How will you make sure your daily choices are as honest, reliable, and secure as the data in your very best experiments? I really want you to think about that as you head into the rest of your week. Thank you so much for joining me in this explainer. Keep asking great questions, and I will see you next time.